So it's a great pleasure for me to welcome Charlie Kane, whom I know for a very long time, and whom I consider to be a young man, because I knew him when he was a graduate student. And he is our this year's Prange Prize awardee. A big occasion for us. It's probably the most important prize on this campus. Certainly the most lucrative, so I think it's most important or not. And he will give his public lecture tomorrow at 4 o'clock in the physics building. But the Prange Prize endowment has 2 talks. One is called a technical seminar. And this is a technical seminar because we active theoretical physicists want something out of the speaker also. So Charlie is telling us something that he did very recently, and I'm looking forward to it. I'm not going to give him a big introduction embarrassing him today. That will be tomorrow. But let me just say he's somebody that I respect enormously for very creative and original thinking. And I say that in all sincerity. Charlie.
Okay, thank you very much, Shankar. And let's see, can I put this on my?
I think so.
Let me know if that's.
Chris will let us know if we're having lapel versus microphone
problems. Okay.
I think should be good.
And I can take this off?
Yes.
Okay, well, that feels good. It's really, really a pleasure to be here doing this. More than usual, because this is the first time I have actually done this in just about 2 years. So it is great to be back out, giving talks, interacting people, and so it just makes me very happy to do this. And so what I want to do is tell you about something that I've done very recently, so this has been one of my pandemic obsessions.
Good, wonderful. So, so as I said, this is what I've been doing over the pandemic, and it's yet another example of a secret that was hiding within band theory, the band theory of solids, and it's something that I didn't realize existed. And the idea is to search for a kind of topological quantized response that reflects the topology of the Fermi surface in a metal. So that's what the idea is going to be. And so I'm going to start off with a simple example of this that is well known, which is basically the Landauer formula in one dimension, and we're going to generalize that to higher dimensions and show that it reflects a property of the a d-dimensional Fermi sea, which is called the Euler characteristic. Okay, and I'm going to motivate this with a simple thought experiment, which is, I think, simple enough that you can know it's right. And then that'll be followed by some more, a little bit more sophisticated calculations. But basically, the thought experiment is the most important thing. Okay, and I'll come up with some ideas about how possibly to measure it. There are going to be caveats and apologies with that. So it may be difficult, but I think this is something that's worth thinking about, how to try to measure that. And there are going to be key issues, which are going to be the role of electrical contacts, the role of electron interactions, and then I think there's food for thought as well for the future. Okay, so let me start off with just the idea of topological quantized response. And let's see, why isn't this going forward?
Sorry, standard problem will be fixed.
Okay, so I can go back and forth now. Good. Okay, thank you.
Had control of the slide.
Okay, so so the hallmark of the idea of topological quantized response is the quantum Hall effect. Okay, and so this is, of course, a famous thing, and the idea is that by measuring the Hall conductivity in a two-dimensional electron gas, you measure it to be incredibly accurately quantized in units of E² /h. Okay, and that discovery, of course, is the discovery that initiated all of the ideas of topology in quantum matter that are so prevalent these days. Okay, and and the thing about this is what this at least the integer quantized Hall effect tells you is it tells you about the topology of the filled electronic states. Okay, and it basically it tells you about the sort of the quantum topology. It tells you how the wave functions of the valence band twist as a function of momentum, and that can be captured by a topological invariant called the Chern number. Okay, so this is this quantized Hall conductance is a very beautiful thing, and it makes you wonder whether there are more versions of this kind of quantization that can occur, and there are, though they come with lower levels of precision, and there are caveats associated with them. An example of that is the quantized magnetoelectric effect on the surface of a topological insulator. So this is something which there's a sense in which it's quantized, though there are caveats associated with that. But nonetheless, this prediction of a quantized a magnetoelectric effect on the topological insulator surface led to a prediction that could be tested experimentally, and there are experiments which have demonstrated this this quantized magnetoelectric effect on the surface of topological insulator. Okay, and so there are versions of there are more versions of this quantization, and I'm going to be exploring another one. Now these effects have to do with insulators. Okay, where you have an energy gap, and you're talking about some topological property of the ground state, basically, or the manifold of occupied electronic states. Now, you could also talk about the topology in a metal. Okay, in a metal, of course, you have states which are filled up to the Fermi energy, and there's a Fermi surface. And so, for example, if you have a Fermi surface in a Weil semimetal. Okay, so a Weil semimetal is a three-dimensional material that has a Dirac point in its electronic, or a Weil point, an unpaired Dirac point in its electronic structure. And if you have a Fermi surface that surrounds it, then that Fermi surface has a non-zero Chern number. Okay, and that shows up in some term in the nonlinear optical conductivity. Okay, and so and again, there are caveats associated with this as well. But this is another generalization of this idea now for a metal. Also, even in 2 dimensions, where you have a Fermi circle, there is a topological piece of the Hall conductivity in 2 dimensions, which reflects the Berry phase that an electron picks up when it goes around the Fermi surface. So there is a topological piece of that. Now, all of the examples that I've talked about here reflect the sort of quantum topology. They reflect the way the wave functions in the valence band or on the Fermi surface twist as a function of momentum in Hilbert space. Okay, they have to do with the phase of the wave functions. Okay, now metals actually exhibit a simpler kind of topology. Okay, which is related to just the shape of the Fermi surface. Okay, so if you look in Ashcroft and Merman, so Ashcroft and Merman, predates all of our talk about topology, but they have a picture of the Fermi surface of copper. Okay, and the Fermi surface of copper has it's basically a sphere, but it has these little necks that go out and meet the boundary of the Brillouin zone. And so the Fermi surface of copper is a topologically non-trivial surface. It has handles. And so you can characterize by a topological invariant, which is the genus, basically the number of holes, and it turns out it has a genus of 4. Okay, so it's sort of like this, sequence of donuts. And so, in the pandemic, I was sitting at home trying to think up things to think about, and I asked myself the question: well, this is a topological property of a metal. What's the significance of that? Could it possibly show up in some kind of topological quantized response? Okay, and so I'm going to tell you the story of what
Can I ask you something?
Yes.
This this fact that this is genus 4. And then if you apply magnetic field, electronic motion will be affected by this topology. This was actually worked in the 60s.
Oh, of course, the Fermi. So Shankar's pointing out that this is well-known physics.
You're talking about something totally
I'm going to be talking about something completely different. Yes, yeah. So it is true that in a magnetic field, then the electrons go around in little orbits, and they are sensitive to the shape of the Fermi surface. Okay, and so there are classic experiments mapping out the shape of the Fermi surface in metals, and
topological terms, exactly using these genesis.
Exactly. That's right. But you see, the thing is, they're not there. It's sort of the brute force measurement of topology, right?
Exactly.
Right. It's not like measuring some quantized response function.
Doesn't come in that description.
Right. That's right. Well, so the Berry phase, the topology of the Fermi surface is not about the Berry phase, because the Berry phase has to do with the phase of the quantum wave function, whereas this is really just the shape of the Fermi surface. So in a sense, this is simpler than the Berry phase in Chernow.
Oh, I see, because it's geometric.
Yeah. Okay. So now, the question is, could this possibly show up in any? Could the topology of the Fermi surface show up in any quantized response? And so my first thought was, of course not. But then I had an epiphany, which is, in one dimension, it's obvious that it's true. And we already know this. So in one dimension, the Landauer conductance of a perfect metal is quantized. Okay, and so let me just remind you about the Landauer formula. It's very beautiful, very deep. And so if you just have a one-dimensional electron gas that's connected between two reservoirs, then so the deep idea of Landau. So we just so we have the energy is just p squared over 2m, right? And so Landauer's deep idea is that the electronic states in the metal are going to be populated according to the reservoir that they came out of. Okay, so that means that the electrons that are moving to the right are going to be in equilibrium at voltage V, whereas the electrons that are moving to the left are going to be at voltage 0. Okay, and so you populate the electronic states to different Fermi energies when there's a voltage difference here. Okay, and so then it's just a matter of, to calculate the current, you just add up the current due to every electron inside the Fermi sea. Okay, so you have an integral over momentum between the two Fermi points of the charge times the velocity. And the magic is that the velocity is, of course, the group velocity of the electron. So it's dE dk. And so the thing that you're integrating is a total derivative. And so you just get e squared over h times the voltage. Okay. Now, this argument is actually exactly the same argument that you can give to explain the quantization of the conductance in the integer quantum Hall effect. It's the same argument. The only difference is that in the one-dimensional case, the left moving electrons and the right moving electrons are on top of each other. Okay. But that fact actually means that this quantization is not as good as the quantization in the integer quantum Hall effect. Okay, because this perfect quantization requires that you have perfect ballistic transport, that there's no scattering. Okay, that electron moving to the right is not going to bounce off of something and turn around and go back to the left. Okay, now one can generalize the Landauer formula to include that fact, and then the Landauer formula tells you that it's going to be e squared over h times the transmission probability for getting across. But if you have perfect ballistic transport and you have perfect ideal reflectionless contacts, then the Landauer conductance is quantized. Okay, just like it's quantized in the integer quantum Hall effect. So you might say, okay, well, it's just like the integer quantum Hall effect. But it's not, because the integer quantum Hall effect is reflecting a topological invariant. But the topological invariant that it's reflecting is a property of the bulk two-dimensional gapped electronic state. It's the Chern number that describes the two-dimensional insulator. We don't have an insulator here. what we have is a metal. And so this quantized response is probing a topological property of the one-dimensional Fermi sea, because it is topological, because it doesn't depend on exactly what is happening under the Fermi energy. I could change the band structure a little bit, and it's still exactly quantized. I could keep changing it, and if I change it too much, of course, it'll change the Fermi surface splits into two. And if I change it so that the Fermi sea splits in half, then the Landauer conductance goes from 1 to 2. Okay, and so this Landauer conductance is probing a topological property of the filled Fermi sea, which in this one dimension is basically just counting how many components of the Fermi sea are there. Okay. And so this fact gave me some hope that maybe in higher dimensions, there could be a similar kind of thing. Okay, and so so this is what I was set out to try to work out. Yes, question.
No, this is totally right, but this looks like when you compare it to the Chern number, this looks like a dynamical phase because it got the derivative of the energy, not say the wave function or the matrix elements of the Hamiltonian, like Chern number has. Is there any?
Yeah, that's right. Well, so I don't know that dynamical is the right word. I mean, but you're right. It doesn't depend on the phase of the wave function. Okay, it's really just counting. It's a property of how many components of the Fermi sea are there. It doesn't matter what the phase of the wave function in the Fermi sea is. So it's different than the Chern number in that regard, where the Chern number really does measure how the phase of the wave function twists as you go around the Brillouin zone.
This here is like the part of the Zach phase, like as you go around the Brillouin zone.
Well, no, this is not a Zach phase. Yeah. So the question that was asked was how is this similar or different to the Chern number? And my answer is that it's very different. And it's different from the Zach phase, which is basically measuring how the phase of the wave function changes when you go around a closed loop. Okay, and this isn't about the phase of the wave function. This ends up being just how many disconnected pieces of the Fermi surface are there.
Sorry, could I ask you something? Because I think you just answered the question. I think the topological number here is the number of pieces of the Fermi surface.
Yes.
It's nothing in the wave function property.
Exactly.
It is just counting the number of pieces of the Fermi surface contributing to transport. Right?
Exactly.
Which is not a property of the wave function at all. It's a
Yes.
property of what the Fermi level is.
Yes, but it is a topological invariant. Okay, so what Shankar said is that, yeah, so this is just counting the number of pieces of the Fermi
And I
surface.
accept it's a topological number.
It's a discrete number. It is a discrete number, and I claim it is a topological number that characterizes the filled Fermi sea.
Nothing to do with the wave function, which you emphasized.
Exactly.
That was my confusion.
Yes, it does not have anything to do with the wave function. Yeah. Okay. So what I want to try to do is I want to ask whether this idea can be exported to 2 or 3 dimensions. Okay, and I think it can. But let me, before I do that, let me just say, I made this point that the Landauer conductance is more fragile than the integer quantum Hall effect. Okay, but that doesn't mean that you can't observe it in an experiment. Okay, and there are classic experiments where the quantization of the Landauer conductance have been observed, and these are classic, 1980s, 1990s type kind of experiments. But so this started with the experiments in a quantum point contact, where you can see as you vary the gate voltage, you're filling up one-dimensional subbands, and you see sort of approximate quantization in units of e squared over h, or 2e squared over h in this case because of spin. Lithographically patterned quantum wires, carbon nanotubes, Leo Kauhoven's semiconductor nanowires. So these all exhibit, if you have good enough contacts and good enough and clean enough. You know, it has to be short enough that you're shorter than the scattering mean free path. Okay.
It's in long wires also with very little resolver. It just has to be ballistic. That's all it is.
Yes, it has to be ballistic. This is a property of ballistic transport. Okay, so so maybe there's hope. Okay, even though it's less robust than the quantum Hall effect. Okay, so so now so here's where I'm headed. Okay, so what I want to show you is that I can define in higher dimensions something that's quantized in the same way, which is, and in d dimensions, what I want to consider is a d+1 terminal nonlinear conductance. Okay.
What does d+1 mean?
Well, in 2 dimensions, it's going to be 3 terminal.
Oh, that's all you mean.
Yeah. In 3 dimensions, it's going to be 4 terminal. In 1 dimension, it's 2 terminal.
Yeah, exactly as it is.
Okay. So this is, you know, so this is the Landauer response in 1 dimension. Okay. So and so what it is, it's going to be, so I have this, you know, so in 2 dimensions, I have 3 terminals. Okay. So basically I'm dividing my 2-dimensional plane into 3 regions. Okay. And I'm applying voltages on 2 of the regions, and I'm measuring the current that flows into the 3rd one. Okay, so that's so I have 2 voltages, and I want to measure a nonlinear conductance, which is going to be it's going to be proportional to the product of the d voltages. Okay, and if these are going at omega, then I'm measuring at the sum frequency. Or I can consider omega to be negative, so that it could be at the difference frequency as well. Okay, so and so this defines a kind of nonlinear conductance.
The word nonlinear is throwing me off. You really mean Landauer is nonlinear than in 1D, the language that.
No, it's linear in 1D,
right?
But it's of order v to the d.
Right, because it's 1D.
So in 2 dimensions, it's going to be a v² response.
Okay.
It's going to be proportional to v1, v2.
What I meant Landauer is nonlinear is I did not make any small v approximation, but it's linear in v by definition in 1D. In 2D, that doesn't have to be the case, but you're saying now you want.
Right, and the higher dimension, it gets more nonlinear. So in 3D, it's going to be v1, v2, v3. Okay. Okay. And so what I have shown, so I can do a calculation of this, and I'll sort of show you that. Is that so if I again do the voltages v1 and v2, and I measure the current in lead 3, which I can think of as the rate of change of the charge, dq dt, then I get a current, it depends on the frequencies. Okay, it's basically V divided by omega, V divided by omega. But it is quantized in terms, in units of, say, E cubed divided by H squared. Okay, and in general, it's going to be E to the d+1 divided by H to the d, and there are powers of frequency here, and you can check that this sort of has the right units at least. Okay, and it's quantized, and there is a topological invariant, which is called the Euler characteristic of the Fermi sea. Now, in 1 dimension, this just reduces to the Landauer response, and this chi-f, the Euler characteristic of the Fermi sea, in 1 dimension is just counting the number of components of the Fermi surface thereof. That's the top. That's the 1-dimensional Euler characteristic, and this generalizes that idea to 2, 3, and even more dimensions. Question?
Yeah. So thinking of V1 and V2 as both small, then this response is second order V. Right?
Yes. So the response.
Would there be like, is this like a subleading term then? Like there'll still be an order V current?
No, not if you correctly define this. Right. No, exactly. So you have, but you have to define it correctly. Then I have to tell you how to define it.
And so then it's harder than to actually measure this. It'd be harder.
Well, no, but no, what I'll say, well, so one thing you can do is you can measure at frequency omega 1 plus omega 2.
Okay. Yeah.
Okay, and that will pick out the nonlinear response.
Right. Okay.
Okay, so in the frequency domain, you sort of can get away with that.
Okay. Cool.
Okay, now, yeah, okay, yeah. So, yes, question. I will tell you that. Yeah. So that, yeah. Another question.
So it seems like human figure doesn't have to be small, right?
Well, if they're too big, then it's just like in the Landauer formula. If you make it too big, then there's going to be a right. Yeah. That's, yeah. So the calculation that I've done is doing a linear response calculation. So what happens at higher voltage, then one would have to think about that. Yeah. Yes.
So is there any restriction on the frequency because in 1D the AC versus DC is kind of
Yeah, and that's one of the caveats that I'm going to have to address. Okay, so there is an issue with the frequency, and that may make this hard. Okay, so but I'll get to that later. Good. Okay, so let me tell you about the Euler characteristic. This is sort of a math thing, you know. So the Euler characteristic is a topological invariant that can characterize any sort of shape. Okay, you know, it can be the shape could be a surface, or it could be just something that has holes in it, and so any Fermi C can be characterized by a Euler characteristic, and so the way you can define it is by introducing what are called the Betty numbers. And what the Betty numbers are is they are basically the number of ways that the Lth Betty number is the way you can make is the number of independent L cycles that you can draw. And so maybe it's best to think of with examples. So in one dimension, so a zero cycle is just a point. And so B0, the zeroth Betty number, is the number of topologically distinct points. And so all the points in one component of the Fermi surface are related to each other. So each segment of the Fermi surface gives you one Betty number. So B0 just counts the number of components of the Fermi surface. Okay. What B1 counts is the number of loops that you can draw that cannot be contracted to nothing and cannot be deformed into each other. So if I draw this hypothetical Fermi surface, in a Brillouin zone, then it has two holes in it. And so I can draw a circle around that hole, and that's one non-contractible loop. I can draw a circle around another hole, or I could draw a loop that goes around the Brillouin zone. And I think you can convince yourself that any loop that you draw, can be deformed out of these. Okay, and so in this case, the first Betty number is equal to 3 because there are 3 independent loops. Then the second Betty number is the number of closed surfaces that you can draw, and there aren't any here because there are no closed surfaces in this two-dimensional Brillouin zone. Everything has, any surface that you can draw on the Fermi surface has to have a boundary. Okay. Of course, if your Fermi surface expanded if your Fermi C expanded to fill the entire Brillouin zone, so you filled the entire valence band, so there's no Fermi surface anymore, then the Fermi C would have the entire Brillouin zone is a cycle, and then there would be a second Betty number. Okay. So, but in any case, so this is what the Euler characteristic, and so what the Euler characteristic is basically it's the alternating sum of all the Betty numbers. Okay, and there's a theorem that says that is a topological invariant. It doesn't change if you smoothly deform your surface. Okay, so now in general, this Euler characteristic, which is a property of the Fermi sea, it should be possible to determine it by thinking about what the Fermi surface is. Okay, so like in one dimension, the Fermi surface is points, and there are twice as many points as there are regions. Every region has two points. Okay, so again, in one dimension, this Euler characteristic is just going to be a number of components of the Fermi sea. In two dimensions, what it is it's basically the difference between the number of electron-like Fermi surfaces and the number of hole-like Fermi surfaces. Okay, and so if you look at this picture again, so in terms of the Betty numbers, it's going to be B0 is 1. There's one component of this, there's one connected component of the Fermi surface, -3 plus 0, so it's -2. And there are two hole-like Fermi surfaces. Okay, and the Fermi surfaces on the left and the right-hand side, they are open Fermi surfaces, and they contribute 0. Okay, they're neither electron or hole. Okay, and so in general, you can by inspecting the Fermi surface, you can figure out what the Euler characteristic is, just telling you the difference between the number of electron-like Fermi surfaces and number of hole-like Fermi surfaces. Open Fermi surfaces contribute 0.
So this is quite magical. So I really do not need to do anything. I just need to calculate this thing. Oh no, that's only d is equal to 2.
Well, in 3 dimensions, in 3 dimensions, it depends on the topology as well. And I'm not going to prove this to you, but there's it's not too hard to deduce that it's determined by the genus of the Fermi surface. So the genus of the Fermi surface, sort of counts the number of handles. Okay, and so in 3 dimensions, the Euler characteristic can be written as a sum over all of the disconnected components of the Fermi surface of the genus of that Fermi surface, 1 minus the genus. So for example, in copper, where this Fermi surface with handles has a genus of 4, then the Euler characteristic, if you include spin, is going to be -6. Okay. Now, so there's a distinction here. I'm talking about the Euler characteristic of the Fermi sea. You could also ask, what's the Euler characteristic of the Fermi surface, which is the boundary of the Fermi sea, and they're related to each other. In one dimension, the Euler characteristic of the Fermi surface is just going to be twice the Euler characteristic of the Fermi sea, just because there are twice as many Fermi points as there are, Fermi, connected components of the Fermi sea. In 3 dimensions, perhaps the formula that the Euler characteristic of a surface is 2 times 1 minus g. So that's a pretty well-known formula. Okay, so they differ by a factor. So in odd dimensions, the Euler characteristic of the surface is just 2 times the Euler characteristic of the interior of the surface. Though actually in even dimensions, in 2 dimensions, there the topologically all the Fermi surfaces are just circles which have Euler characteristic 0. So the Euler characteristic of the Fermi surface in 2 dimensions is 0. Okay, and so that's why I need to distinguish between the boundary and the interior. The interior actually has a little bit more information in it in 2 dimensions. Okay, so that's what the Euler characteristic is. Now, there's another way you can think about this. Okay, which is Morse theory. Okay, and so what Morse theory tells you is that you can understand the Euler characteristic of some region if you can understand the critical points of a function that's defined on this region. And we have a natural function which is E of k, the energy dispersion. Okay, and so the energy dispersion is a natural Morse function. And so what Morse theory tells you is that you can determine the the Euler characteristic by just examining the critical points in the electron dispersion. And the critical points are the places where the velocity is 0. So they're either a minimum, a maximum, or a saddle point. Okay, and so the theorem is that the Euler characteristic is the sum over all the critical points enclosed inside the Fermi surface of either plus or minus 1, where the plus or minus 1 basically is telling you how many downward directions there are. Okay, so in 2 dimensions, if you have a saddle, then that critical point contributes -1. Okay, and so this actually makes complete sense, because so if you think about, you know, how can the topology of the Fermi surface change? Okay, so imagine that if you have a saddle point in your electron dispersion. So if your Fermi surface is a little bit below the saddle point, then you know, the Fermi surface is sort of split into 2 pieces on either side. And as you raise the Fermi energy through the saddle, then those 2 pieces are going to connect to each other. And so that is a change in the topology of the Fermi surface. Okay, and these changes in the topology of the Fermi surface, so Shankar, that this is also another old story. This is old enough that this is named after an old guy. So these are so these are called Lifshitz transitions. Transitions where the topology of the Fermi surface changes. And so it makes complete sense that you can understand the topology of the Fermi surface by just thinking about the critical points in the band structure, because the Lifshitz transitions occur precisely when critical points pass through the Fermi surface. Okay, and so this is a useful way of thinking about the Euler characteristic. Okay, so let me so I want to try to convince you that this shows up in some nonlinear response. And so what I want to do is I want to develop a way of thinking about this. Okay, and I'm gonna introduce this way of thinking about it in the one-dimensional case where we already know everything. Okay, and then this will allow me to generalize the idea to higher dimensions. Okay, and so in one dimension, I want to think about the following thought experiment. And this thought experiment is really kind of inspired by Laughlin's thought experiment for understanding the quantization in the integer quantum Hall effect. Okay, it's really the same kind of idea. And so what I want to do is I want to have my one-dimensional electron gas. Let's suppose it's an infinite one-dimensional electron gas, which I divide into 2 regions, the left side and the right side. And what I'm going to do is I'm going to apply a voltage pulse to one side. So I'm going to apply a voltage V for a short time in such a way that the integrated weight of the voltage, the integral of V dt, is equal to h over E, sort of a quantum of voltage in a way. Okay, and so another way I could say is, what I'm really doing is I'm applying an electric field on the boundary here, as a function. So the electric field is then a function of space and time, and it integrates over space and time to h over E. So this is exactly the same idea that Laughlin had when he had a disk, and he threaded 1 quantum of magnetic flux through the disk, and that generates a voltage pulse that's just like this. Okay, so what does this voltage pulse do? Well, it gives an impulse to the electrons and moves them over a little bit in such a way that precisely 1 electron is transported into the right lead, and 1 hole is transported into the left lead. So how can you understand this? Well, so the impulse, so the electric field is going to give rise to a force. Okay, and there's going to be an impulse which tells you the change in the momentum, and so you can work out what the change in the momentum is going to be, and it's basically exactly h bar times 2kF. So it means that exactly 1 electron crossed the Fermi surface because of this impulse. Okay. Another way you can think about it,
So this should be completely destroyed in the presence of any backscatter, any increase.
in the absence of any backscattering. That's right. So everything is happening under the Fermi surface in a way. So the way that I like to think about this is that what you're doing when you apply this this electric field, what you're doing is you're basically, every electron is being accelerated by exactly one space. Okay, so the electrons are filled up, and every electron is moving over by one space, so that at the end of the day, there's one extra electron at the right Fermi point, and one unoccupied, one state that one extra hole basically on the left point. Okay, and you see, and what this is reflecting is actually the chiral anomaly. Okay, so the chiral anomaly tells you that if I just think about the number of electrons, say at the right moving Fermi point, it's not conserved in the presence of an electric field. And the non-conservation of that is precisely characterized by the fact that if I apply an electric field, then there's going to be a flow of electrons into that Fermi point, which is precisely one electron per every h/e of integrated electric field you get. So this is telling you precisely the physics of the chiral anomaly, which is the same physics that underlies the quantization in the integer quantum Hall effect. Yes.
The bottom picture is transfer of projection in momentum space to the right.
Yes, exactly.
The top picture is transfer of projection in the real space.
Yes.
Across the boundary.
That's, yeah. So Victor's point was that, so this picture is in momentum space where I transfer one electron from the left moving Fermi point to the right moving Fermi point. Okay. And so the question is, okay, so what happens in real space after I do that? Well, there's going to be one extra right moving electron. Where's that electron going to go? It's going to go to the right. And it's going to end up in the right lead. The extra hole is moving to the left. It's going to end up in the left lead. So the conclusion of this is that after the, so if I do this voltage pulse, and then after the pulse is over, I measure the charge in the right lead, there's going to be one extra electron. Okay, so that's the resolution. Okay. One more way I can think about this, okay, which is useful, is that so the chiral anomaly, what it's telling you is that the right moving and the left moving electrons, they're actually connected to each other. Okay, and they're connected to each other precisely at the critical points where the velocity is zero. You see, those are the points where an electron changes its mind and turns from being a left mover into a right mover. So another way I can ask, and basically, every right mover is going to end up in the right lead, and every left mover is going to end up in the left lead. And so if you can get an electron to change its mind, then it'll change the charge. That's going to be what changes the charge that goes into the leads. And so another way of thinking about this is that you can just count, every electron, because of this voltage pulse, moves over by one space. And so that means that one electron is going to change directions at every critical point. Okay, and they're going to change directions either to the right or to the left, depending on whether it's a maximum or a minimum. Okay, and so one way you can understand this charge that gets transferred to the right is it's going to be the difference between the number of minima and the number of maxima, which is 2 minus 1 in this picture. Okay, which is the Euler characteristic from Morse theory. Okay.
It looks sort of like a Newton's cradle in momentum space, the way you draw it. It's if you think of the electrons being identical part of this. Like,
yeah, sort of like that. Yeah. So the point, the observation is that this sort of looks like a Newton's cradle. Yeah. Okay. So now, so I want to tell you my idea for how this generalizes in higher dimensions. Okay, and so this slide is going to be the most important slide. So if I don't finish the rest of my talk, this next slide is the take-home message. Okay, so so here it is. So what I want to do is I want to now imagine I have a two-dimensional plane, and I'm going to define 3 regions in this two-dimensional plane. And for convenience, I'm going to define one region to be the entire, left-hand half plane, and the other 2 regions to be the other 2 quadrants. Okay, and so what I want to do is I want to do a sequence of 2 pulses. First, I'm going to apply an H/E voltage pulse to region 1, and then I'm going to apply an H/E voltage pulse to region 2. Okay. And so both of those pulses are going to cause some electrons to move, go in different directions. And what I want to do is I want to calculate the charge that goes into region 3 that is due to both pulses. So I'm going to compute the charge Q3, but I'm going to subtract off the charge that I would have gotten if I'd done either of the pulses alone. Okay, and I claim that that is going to, and that, that by definition is going to be of order V1, V2. Okay, and now of course, if you were going to really do this experiment, then you'd have to do a subtraction, which is hard. But I will argue that if we do it in the frequency domain, then we can look at the sum frequency. Okay, but let me try to convince you with this that this voltage pulse leads to the quantized result. So the first pulse. So the first pulse, I have, I have an electric field along the entire y-axis, and so KY is still going to be a good quantum number. And for every value of KY, it's just like the one-dimensional case. And so after the first pulse, then for every value of KY, there's going to be 1 extra electron moving to the right and 1 extra hole moving to the left. Okay, all I care about are what's happening on the right-hand side, because the ones moving to the left, they're going to be gone. They're not going to be affected by the second pulse. Okay, so in this picture, here's another hypothetical Fermi surface. So after the first pulse, then I'm going to have extra electrons everywhere in this sort of shaded region on the right moving side of the Fermi surface. Okay, I have 1 extra electron for each of those. Okay, so now I'm going to apply the second pulse, which is a pulse in region 2. Okay, and and all I care about is the effect of that on the extra electrons that the first pulse gave me. So I want to ask, what happens to these electrons? So now those electrons are going to get an impulse in the y direction. So they're going to move up by 1 space. And so in order to figure out the net charge that goes into this, what I need to do is I need to determine how many of those electrons change direction. Okay, the electron that's up here, it's definitely going to go into the up lead whether I apply the pulse or not. The electron that's here is definitely going to go into the bottom lead whether I apply the pulse or not. It's only the electrons right at the side of the Fermi surface that are going to change their minds. Okay, and so what I will argue is that in order to figure out this charge, what I need to do is I need to count the critical points on the side of the Fermi surface here, where the velocity is pointing straight to the right. And I need to I need to calculate the difference between the number of ones which are concave minus the ones that are convex. So the ones that are concave, that means that if you look at the dispersion as a function of ky, it's going to be a upward parabola. So it's going to go in this direction, whereas the concave down ones are going to be a downward parabola as a function of ky, and so they're going to change velocity in the opposite direction. Okay, and so the upshot of this is that we can there's going to be some number of electrons which go into this lead 3, and I can determine that by counting the difference between the number of convex critical points and concave critical points on the right-hand side of the Fermi surface. Okay, now, so if you stare at this for a while, you can convince yourself that this is actually a topological invariant, which is the same as the Euler characteristic. So let's just look at this for this picture. Okay, so so what this is going to be, I have two of these, two concave critical points and 3 convex critical points. So 2 minus 3 is minus 1, which is exactly the Euler characteristic of this Fermi surface, which I can think of as the difference between the number of electron and hole Fermi surfaces. There's 1 electron Fermi surface, 2 hole Fermi surface. So it's 1 minus 2. Okay, and so I will argue for any Fermi surface that you draw, if you do this construction, you will arrive at the Euler characteristic. Okay, so this is the argument. Now let's see. So what time should I finish? 12:05. Okay, so I have, because so let me just so this is a sort of a heuristic argument, which I think is right, but one can also do a calculation. Okay, so let me just tell you the kinds of calculation that you can do. So the simplest thing to do, which really is the right calculation to do, is since there's no scattering, is to just do Boltzmann, is just do semi-classical Boltzmann theory. Okay, and let me not dwell too much on the technicalities of this, but you see, if since there's no scattering, the electron distribution function is just going to obey the Boltzmann equation. Okay, and it's pretty easy to solve the Boltzmann equation perturbatively. If I have these electric field pulses which are living only on the boundaries here, then it's pretty easy to solve the Boltzmann equation order by order in the electric field. Then you just have a couple of integrals to do, and you end up with an integral over the Fermi surface that looks like this. And what this integral does, if you look at this integral, what you can see is that it exactly summarizes the counting the critical points on the Fermi surface that I did on the last slide. Yeah, Victor.
So what is the definition of letter Q, this capital Q? What is it exactly? The definition, yeah, capital Q.
Yeah, so what it is the excess charge in the third lead, defined as the charge in the third lead minus the charge in the third that I get if I did either of the pulses independently. So it's going to be so what I'm doing here is I'm solving the so after the first pulse, I have a distribution function which is going to be the equilibrium distribution function plus a delta F, which is of order E1. Then after the second pulse, I'll also have a distribution, but what I'm going to do is I'm only going to use the delta F in order to calculate the delta F1 in order to calculate the delta F2. So then I'll have a distribution function which is of order E1, E2, and then I use that to compute the charge, by integrating over the region 3. Okay, so that's, yeah. Okay, so I can do that calculation and it reproduces my heuristic argument. And there's one more manipulation that you can do to this that turns it into precisely counting the critical points in the bulk of the Fermi surface. Okay, and so it really is the Euler characteristic. So we can generalize this to so one thing is that this is particular for this geometry where one of the regions is sort of the half plane. So I can generalize it to arbitrary angles between the regions. So there are arbitrary rays going off in different directions. And I can also, it's also straightforward to do the to solve the Boltzmann equation in the frequency domain. So now I have my electric fields, which are going to be E the I omega 1 and E the I omega 2, and it's the same calculation basically. Yeah, Victor.
If it's in frequency domain, then generally we deal with complex phases. Now it can be phase shift. I mean, you have frequency, you have components V1 and V2. They have frequency, or because they have different frequencies, there is no phase shift.
Well, there will be. I mean, so you have to keep the phase shift in the calculation, and it'll.
I mean, they will be complex in general.
Yeah, that's right. So in general, so yeah. So if V1 and V2, if like omega 1 is equal to minus omega 2, then you have to worry about the phase difference between the omega 1 and omega 2, right? So yeah, the phase of this could matter if there's some interference. But yeah, so yeah. Okay. Yeah, it's all included in the calculation. Yeah. Okay. So there's one more calculation you can do. Okay. Which is a little bit more involved, which is to do the quantum version of this. Okay. You know, for the Landauer, calculation, you can do the Kubo formula, which is just linear response theory. So you can do the same thing, do perturbation theory in these voltages, and what you end up doing is calculating a diagram that in 2 dimensions has 3 legs on it. Okay, and the thing that I realized that this diagram actually has a topological piece in it that knows about the Euler characteristic of the Fermi surface. Okay, and it's sort of in here, so one can do. I don't want to get into the technicalities of this, but one thing I'll say is that, I mean, this calculation ends up giving exactly the same answer that the Boltzmann equation did, and it had to, because there's no scattering. Okay, and so we didn't really learn anything new by doing this calculation, other than that there's sort of a topological piece to this triangle diagram that I don't think was really known before. Okay. Yes.
Are these the results of perturbative or non-perturbative?
Perturbative in V.
Yeah.
Yeah, that's why it's of order V squared. Yeah. Yeah. So I'm doing perturbation theory in V. That's yeah. Yeah, that's right. That's right. Yeah. Yeah. So I'm calculating. Yeah. So this response function, the thing that I'm calculating is that there is the response at order V1, V2. Yeah. Okay. All right. So yeah, let me just so there's a question, can this be measured? Okay, and there are tricky issues with that. And so let me tell you one of the tricky issues. Okay, one is the role of electrical contacts. And so this is where, in one dimension, you can take the DC limit and measure the DC conductance. Okay, and in fact, that's the most robust thing to do, is to measure the DC Landauer conductance. So here we do not have that luxury. And the simple way to think about it is to think in this pulse construction, right? So I'm applying a pulse, then I'm applying another pulse and asking what charge goes into the third contact. So let's imagine that now I have, I divide my 2-dimensional electron gas into 3 regions, which I cover with metallic contacts, which are then hooked up to your voltmeter, right? You have to have contacts. And I apply a voltage pulse on one of the pulses, on one of the leads, and then I wait for a day, and then I apply the next pulse. Okay, so what's going to happen, right? After I apply the first pulse, everything's just going to go off into the leads, and then you've completely forgotten about the pulse by the time you apply the second pulse. Okay, so it's clear that the two pulses have to be timed so that the electron, the electrons are still in the sample when you apply the second pulse. Okay, and so if there's a dwell time, which is how long the electron stays in the two-dimensional electron gas, then I have to have the two pulses be within that dwell time. Or in the frequency domain, there's a limit to how low the frequency can be. If I take the DC limit, then that's like taking the time between the pulses to infinity. Okay, and then we lose it. Yes.
So the T2 minus T1 less than tau, that's understandable. I don't want to lose memory. The second equation. But first.
The first equation is that if I measure the charge too soon, then the electrons might not have gotten into the third lead yet.
So T3 is when you measure
the charge. Yeah.
So T1, T2 when they apply voltages.
And then I measure the charge at time T3.
Charge at T3.
Yeah, and I need to wait long enough so that I count all the charge that's eventually going to get into lead 3.
So it's quite tricky.
It is tricky.
Neither a weak tunneling limit nor a strong tunneling limit to the leads, because you have two different time states.
Well, I want a weak tunneling limit, but I want a large area.
Yeah, okay. But usually I think of the lead as giving a tunneling amplitude. I don't think in terms of a tau, right? I mean, you put a lead.
Well, no, but if you have a lead that's over a large area, okay, but it's very weakly coupled, then the electron will travel a long distance, but it'll eventually tunnel into the lead. Okay, so that's the regime that I kind of want to be in. Now, I'll say it's conceivable that one could do a kind of an experiment by just having capacitive coupling. Okay, one might be able to do something with like that as well. But this is a tricky thing where I think it's going to require.
Principle is perfect. It can be done.
Yeah. But I think it'll require some experimental ingenuity in order to do. Yeah.
But the bottom equation, Luke's natural limit would be omega 1 equal to omega 2, which will naturally satisfy the bottom equation. So take two frequencies equal.
Yeah.
Right, and then you phase shift perhaps.
Yeah, well, one could possibly do that. Yeah, there's tricky. Yeah. So because if they're equal to each other, then I think the current is going to actually be zero. Yeah. Then there'll be a charge, but there won't be a current.
Circular polarization. We have two perpendicular direction shifts that have been circular polarization. Yeah. Breaks time reversal, so can generate current. Something along those lines.
Yeah. Right? Yeah. So so this is a tricky thing. So but let me just so let me tell you, there's one other trickiness, which is think about electron-electron interactions, and so they actually have an effect. Okay, and this effect is actually something that's well known in one dimension. Okay, and in fact, there's an old paper that I know Shankar knows about. This old paper where if you do this, the kind of calculation that I'm telling you I did here, if you do that in one dimension, calculate the Kubo formula conductance of a one-dimensional system that's interacting, then it actually depends on the electron-electron interactions through this Luttinger parameter K. Okay, now that's actually not the right answer for when you measure the DC conductance with leads. Okay, with leads, you actually, in the DC limit, even with interactions, you get E squared over H. Okay, and there's an order of limits question about whether you take the frequency to 0 first or the length to infinity first. Okay, we have the same problem here, but we don't have the luxury of taking the frequency to 0. Okay, and so that's a problem. Okay, which means that in order to observe this in a two-dimensional electron gas, you want to have something that's weakly interactive. Okay, but maybe graphene could do this. Graphene, close to the Dirac point. If I have a finite short-range Coulomb interaction that's maybe screened by the metallic leads that I have, so it's short range. The density of states near the Dirac point gets very small, so the interactions should be weak. And the prediction is that depending on whether the Fermi energy is on the electron side or the hole side, the topology of the Fermi surface is different. Okay, and so we predict there should be a jump in this nonlinear conductance. Okay, so maybe this could be measured. One has to think. There are lots of experimental issues I think that would have to be resolved to do that. Okay, so I'm basically done now. So let me just say I think this opens many more questions. So one question is, are there other probes of this Euler characteristic? You know, this Euler characteristic is a fundamental thing that characterizes a metal. Are there other ways to get at it? You know, maybe some thermal conductance. You know, there's a quantized thermal conductance in one dimension as well. Okay, can we generalize that? And actually, that does not depend on interactions. So it doesn't depend on the Luttinger parameter in a Luttinger liquid. And there's also an issue is, you know, is there something deeper about this Euler characteristic? Is it telling us something deeper about the ground state of a system? You know, because it's a kind of a generalization of the chiral anomaly. You know, the chiral anomaly tells you about the critical points where the left movers and the right movers are touching each other in one dimension. This thing is telling us about the critical points where all of the different directions of motion are touching each other. Okay, so it sort of kind of smells like this. Another interesting thing to think about is quantum entanglement. You know, there's this famous result in one dimension. If you have a one-dimensional conformal field theory, then there's a universal bipartite entanglement entropy, or at least the coefficient. There's a log divergent entanglement entropy, and the coefficient of that log is universal. And so it's and this C in one dimension is just chi-f. It's just the Euler characteristic in one dimension. So perhaps in higher dimensions there's some characterization of the higher dimensional quantum entanglement that some universal characterization that is determined by the Euler characteristic. And you know, and then that invites one to think, well, if we can do that for a Fermi liquid, could this be used to characterize more general, strongly interacting states of matter? Okay, so I've gone over. I apologize. So again, thank you so much. This was really fun. So it's a pleasure.
Time for a few questions. I have a question, so I want you to take one. Yeah. So Charlie, it's very nice as usual, beautiful. But one thing that's slightly bothering or worrying me, and I want you to put me straight. Suppose everything works here. What have I learned more than what I would learn by doing Fermiology, the genus of the Fermi surface? Yeah, I'm going to see jump, I'm going to see all kinds of things. But in the end, am I being too harsh if I say this is a very beautiful way of doing Fermiology?
Well, okay. I mean, that's a valid. You're making a valid point. So let's suppose in the 1960s they did the experiment which mapped the Fermi surface completely. So you knew everything about the Fermi surface. You could determine that number. Okay, that's true. That's true. So, but I think the question is what is that this tells us that number has a new significance. Okay, and you know, so perhaps that could lead us into some more general way of characterizing quantum phases of matter.
It's not the same thing.
Yeah.
It's looking at it in physics. Theoretically, if you want to look at things at deeper and deeper level, it's a bit deeper. But those genuses would determine.
Look. I mean, you're not going to learn the genus of the Fermi surface by doing this experiment. Right. That's right. But look, you're not going to learn the Chern. I mean, you know, you could make the same argument for the Chern number. I mean, of course, now there, of course, the Chern number was measured first, right? And then that.
Believe me, I have made that argument.
Yeah.
And the related question is, again, you talked about interaction. The disorder issue here is crucial.
Oh, it is. Yeah.
It has to be all in the ballistic limit.
Yeah.
And there'll be corrections coming from.
Yes.
Because nothing is infinitely ballistic.
Absolutely.
And those corrections, I think the kind of diagrammatic thing we have done can tell us something about the size of those corrections.
Certainly. So certainly that is, you know, if this turns into something which is remotely feasible, then those will be very important kinds of things to do.
Graduate students to do. I mean, seriously.
Yeah.
Because it's not the end. It's in some sense the beginning.
Yeah. Thank you. Yes.
Sorry, maybe I can flip around the question about doing fermiology actually. So if you imagine doing this measurement and then doing some quantum oscillations measurements, which is in general a very hard inverse problem to turn quantum oscillations into a Fermi surface, is the genus, or sorry, is the Euler characteristic something that would simplify that inverse problem?
Well, I don't think it would tell you anything about the Fermi surface other than the Euler characteristic.
Sure.
So to the extent, I mean, so you're saying you have all this data from the quantum oscillations, and you're trying to back out of that the shape of the Fermi surface.
Yeah.
Okay, and so it certainly will give you a constraint that the Euler characteristic has, but that may not be the biggest thing that you need to know in order to constrain. I'm not sure it would help you that much. Yeah. So the question is whether doing this measurement could help interpreting the quantum oscillation experiment, and the data that you get from quantum oscillations. And yeah, I'm skeptical about that.
Bill has a question here on Zoom.
And I don't know where to look, but I'll look at the camera. Yeah.
Right. Anyway, this is Bill Phillips. So I want to explore a little bit more your last point here about generalization to non-Fermi liquids. Now, the way you presented this initially, at least, it's a pretty classical phenomenon, or at least that's the way I saw it. And on the other hand, when you presented the picture of the Fermi sea, you were looking at something that looked like a quantum degenerate gas. Now, of course, it's not hard to have a quantum degenerate gas of electrons, but if this weren't fermions, if this were, say, bosons, then are you thinking about a Bose condensate? Are you thinking about?
Well, let me tell you how this goes in one dimension. Okay, so in one dimension, for free fermions in one dimension, we have this Euler characteristic, that generalizes to this if you have a conformal field theory. Now, free fermions in one dimension are a particularly simple example of a conformal field theory that has C equals 1, or C is equal to the Euler characteristic. But there exist strongly interacting phases of matter that could have different values. Okay, and those are interesting things to think about. And so so C equals 1/2, for instance, for Majorana fermions. Okay, so I guess my question here, and I don't really have a specific thing in mind here yet, but my question is could there be phases of matter which are not Fermi liquids that still have something which is analogous to this Euler characteristic, but maybe it's not an integer anymore?
Well, part of what I'm wondering is, do the quantum statistics of the particles play a role in what happens? Would this work just as well with bosons, for example?
Well, yeah, I'm not sure about that. I mean, so certainly for fermions, you have the notion of a Fermi surface.
Right.
Okay, and for some phases of matter, this Fermi surface, maybe you could have like a spin-on Fermi surface or something like that, where you have something which is analogous to a Fermi surface that could have a similar characterization. Now, how far you can go with this, I don't know. I don't know. So if you have a system of interacting bosons, of course, you could have a system of interacting bosons that strongly interacting that could have a Fermi surface as well, right? I mean, but
sure, if they were fermionized, then they would look an awful lot like. But what if they were non-interacting bosons?
Yeah, I'm not sure I see this applying to that. Yeah. Yeah.
Trivial, basically.
Yeah, I don't see that applying here.
Okay.
Yeah. Let's see, we have another question here. Yeah.
So what happens if you have finite temperature? So the vacuum surface is not gas anymore?
Yeah, if you have finite temperature, yeah. So obviously, if the temperature is too high, it's going to mess it up. But so actually, Landauer kind of survives at finite temperature. I'd have to think a little bit about whether this does. I suspect it's probably more fragile, but I don't know.
Actually, this is quite subtle, as you know, that quantum point contact experiment doesn't work at ultra-low temperature because you have all these resonances.
Yeah.
Okay. Temperature is essential. And I was just wondering, that's really my student, I was going to ask him to look at high dimensional temperature terms. I mean, Songhe and I looked at it and we found temperature is essential to see the quantization because otherwise you're dominated by.
It could, well, certainly. I mean, yeah. If you go to too low temperature, then there are other pieces of physics associated with the fact that you don't have a pristine system.
Precisely.
Yeah.
So the question now is that if something like this we hear, some set temperature adjustment will necessarily also.
Probably, yeah.
So it's not a trivial issue to figure out what temperature to do.
Yeah.
Offhand.
Yeah. One can certainly, I mean, so one simple thing I can do, which I haven't done, is to do the linear, is to do the response theory at finite temperature.
Putting in the Fermi distribution.
Yeah.
That's the first thing.
Yeah.
And also give the quantum calculation that we do.
Right. Yes, another question. Well, yeah. So the upshot is that let's see. I can't go back. So the question is the role of interactions, and the answer is yes, they do have an effect on this nonlinear conductance. Okay, and a simple-minded estimate says that basically the question is what's the strength of the interaction times the density of states. Okay, and now in one dimension, this is an old story. So if you do the naive linear response calculation for the conductance, which is this calculation that I did 30 years ago that Shankar knows about, then what you find is that there is an interaction correction, which can be described as in terms of this Luttinger parameter. So for weak interactions, the Luttinger parameter is going to be like this. Okay. Now, it turns out when you do the DC conductance with leads, there's a subtlety associated with that. And in a sense, the resolution is that in the leads, you really have it's as if you have non-interacting electrons in the leads. So in the limit of low frequency, what you're really sensitive is to what the electron-electron interactions are deep in the leads rather than in the sample. And so you go back to the pristine non-interacting result. Okay. Oh, are you saying that should the interactions get stronger at a Lifshitz transition? So let's see, I guess it depends on the dimensionality, right? So in one dimension at a Lifshitz transition, you have a square root divergence of the density of states, right? In 2 dimensions, the density of states stays constant. And in 3 dimensions, I think you get a square root. It goes to 0 like a square root. So, so you might say that in 2 dimensions, it's marginal. And in 3 dimensions, maybe the interactions are weaker close to the Lifshitz transition. Okay, yeah, so I don't know about that. Yeah, it could be that they're marginally relevant. That's possible. Yeah. So I haven't looked at it at that level of detail. Yeah, yeah. Good question.